All right, so far we've developed the idea of the wave function, looked a little bit at how to get that by finding solutions to the Schrodinger equation. And then last time we looked at how to calculate expectation values and relate those to the expected results for measurable properties, right? What we haven't done so far is to look at an actual system, something that is real in any sense of the word, right? We've concentrated on sort of made-up wave functions that, for the most part, I picked for simplicity so that we could easily see what was going on without having to do a lot of overly difficult math. In this segment, what we're going to do is talk about a real case for the first time, the hydrogen atom, right? The course is about chemistry after all, and so we should look at things like atoms and molecules when we're able, and it's time to do that today. So first up, atoms are going to be three-dimensional, right? We expect our hydrogen atom to be spherical, and so we'll need to have a three-dimensional set of coordinates, a three-dimensional problem, right? The Schrodinger equation is going to get us the energy of the electron in the hydrogen atom, right? And so our coordinate system is going to put the nucleus, the proton, at the origin, and then the electron will be at some distance from the origin, all right? The proton is thousands of times heavier than the electron, and so it's reasonable to treat the proton as stationary and let the electron be the thing whose position is described by the coordinates, right? Our electron will have kinetic energy, and it also have potential energy, where the potential energy comes from the charge interaction between the positively charged proton and the negatively charged electron, right? That potential energy is just given by a Coulomb equation, and that's on the slide now, right? So it says that our potential energy V depends on R, the distance from the proton to the electron, right? In that equation, Q1 and Q2 are the charges on the two particles. In this case, those are equal and opposite, right? Because the charge on a proton and electron are the same magnitude and just opposite signs. The epsilon naught in the denominator there, that's a physical constant known as the permittivity constant, and R is just the distance between the proton and the electron, right? As you can see in that, the only coordinate or the only thing that determines that potential energy is the distance, right? It doesn't matter what direction the electron is from the nucleus. It only matters how far away it is, right? So the atom should be spherical as a result. And because of that, spherical coordinates are sort of a natural choice. It is just about always the case that if you choose a coordinate system that has the same kind of symmetry as the problem you're working on, that various aspects of the problem will get simpler, right? And that's true in this case. So this problem for the hydrogen atom is invariably set up in terms of spherical coordinates rather than Cartesian X, Y, and Z coordinates. Okay? So let's take a quick refresher about spherical coordinates, right? Spherical coordinates are really three-dimensional polar coordinates, right? So if I have a point, the point here that is marked as R, say, marked, well, the R is the radius, right? That point that's on the end of the vector, we'll highlight that point. R is the radius, that's the distance from the origin to the point that we're picking out. And then theta and phi, as marked in the figure, give us two angles that are the rotations of that vector away from two of the three axes, right? If I specify R, theta, and phi, I have three coordinates, and so I've specified my point in three-dimensional space. One thing we're going to need to work with is the volume element in these spherical coordinates, right? Because now our wave function is going to tell us, when we take the square of the wave function, it's going to tell us the probability of finding the electron in a region of space near a particular point. The coordinates are now three-dimensional, and so our region is going to be a volume element rather than a length element, all right? The important part of that, for what we're working with right now, is going to be the fact that if I only know R, because R is the only variable that's going to show up in my Schrodinger equation, right? If I know R, then I know that my electron is somewhere on the surface of a spherical shell with that radius, right? So if instead of knowing r, theta, and phi, I only had r specified, then I know that my point is on the surface of a sphere at that radius, okay? The issue comes that the bigger the radius is, the more points there will be on the surface of that sphere, right? In the limit that r is 0, then we have just one single point. That's the origin, right? And so there's only one actual location that gets me r equals 0. If r gets larger, then there are more and more points on that spherical shell, right? And so the volume of that spherical shell is going to be 4 pi r squared dr, okay? Where that's what we'll have to use when we want to get a radial probability function. If we were going to be working and integrating over all three variables, we would need the one down here, which is dv is equal to that r squared dr piece. We now have the sine of theta and d theta d phi. If we integrate over the angles, that's where the 4 pi actually comes from in the 4 pi r squared dr piece, right? And so the volume element is going to be an important part of how we calculate these things. So we're not going to actually work through how to solve the Schrodinger equation for this this particular case, all right? Depending on how comfortable you are with differential equations, you might feel able to do that, but we're just going to go with declaring that the lowest energy solution, the ground state, what we would normally label as psi 1s, because this is what we call the 1s atomic orbital, is got the form written here, right? So the first thing I notice if I look at this equation is, although over here it says it's psi of r, theta, and phi, those are my coordinates, the only one of those coordinates that shows up in my equation is actually r, right? There are no thetas and phis in that wave function. And if you think about it even for just a second, what that tells us is that's the familiar result that s orbitals are spherical, right? So this orbital is got no directional preference because it has no directional coordinates in the expression for it. The other thing that's in there that we may not have seen before is that A0. That is the so-called Bohr radius, which is equal to about 53 picometers. And that is actually also equal to this cluster of constants here, right? Where m sub e is the mass of the electron, e on the bottom, e squared, that's the electron charge. There's an h bar up top, and there is again that permittivity constant, epsilon naught, all right? That chunk of things occurs often enough, and as you can see, just looking at the equation above, the equation does look a lot more friendly with A0 in there instead of having that clump of constants in both places that it's got A0s, right? All of that comes to about 53 picometers. It's definitely got to have distance units, because if you look up here, you'll see we've got an exponent that's r over A0. Exponents have to be unitless, right? So that means since r is a distance, A0 has to also be a distance, okay? And the term that is the Bohr radius, that comes from the Bohr model of the atom. And that was Bohr's radius of the first orbit in his model, which features like these sort of circular orbits around the nucleus. It's a model that has a lot of things not quite right, although it does also mimic a lot of physical facts. And so it's mostly of historical origin at this point. So that gives us an equation for the wave function. It's just an exponential decay, right? If we look at it, the piece out in front, that 1 over pi A0 cubed, square root of all that stuff, that's the normalization constant that makes sure my wave function would integrate to 1 if I integrate that over the entire coordinate space. This plot has two different things on it, okay? And so we're going to spend a couple minutes talking about what's going on here. The red plot in there is actually the wave function, right? That's the 1s wave function plotted, and you can see it's just an exponential decay, right? Its maximum is actually at the origin because that's the way exponential decays should work, right? The x-axis on this plot for both curves is in units of A0. Okay, and so this goes from the origin at 0 it goes out, the whole graph runs out to 20 times A0, although all the action is pretty much inside of 8 A0, it looks like, just from what we've got there, right? The y-axis here is essentially in arbitrary units because we've got two kind of different quantities plotted on there. The red line is just plotting the wave function, right? So that's just the shape of the function that was there, and you can tell it just looks like an exponential decay, which is what the function was. The blue curve is what is known as the radial probability function, okay? And so that blue curve, this one, is actually plotting, that is my 4 pi r squared psi squared, okay? So that's what the probability function should look like. Notice that the wave function itself has its maximum at the origin, right? The probability function has its maximum out here, and that's actually right at A0, right? So it's right in the middle of that chunk there. The most probable radius for the hydrogen atom 1s orbital is actually A0, the Bohr radius. Okay, how can that be? That's because when I make that blue plot, I've got the exponential decay, which is psi is exponential decay, right? This one here, this is just psi. But if psi does that, then psi squared looks more or less the same, right? Psi squared is still got a maximum at the origin and decays more sharply from there, right? So I have psi squared, which is decaying. I have r squared, which is increasing, and that's why I get a maximum when I put those things together in there, right? Way to interpret that is to say that as the radius gets larger, there are more and more points, right? So at the origin, there's really only one single point. And so even though that's the maximum value of psi, and therefore of psi squared, the fact that there's just one point there means the overall probability for the electron being at the nucleus is very, very small. Right? As I get further away, there are more and more different points at that same radius, and that is what leads to the maximum showing up there, right? And if we actually do the math, which I think we will in a moment, we'll find that that should work itself out to happen where that maximum is at distance r equals A0. Okay, so the probability density is highest where psi star psi, it should really say that I should really have the r squared piece in there because otherwise it doesn't quite work that way. And that happens at r equals A0, okay? The average distance from the nucleus, if I was to find the expectation value for the distance from the nucleus, that's not really going to be the same. And the reason for that, if I toggle back for a second, is if you look at the blue curve on here, this is the maximum, right? And it's clear looking at that there's a lot more area on the long side of that curve than there is on the short side, right? And so although that's the most probable point, the electron is more often going to be at larger radii than that, rather than smaller radii. That means the average radius is going to be tugged out towards longer distances, right? So the expectation value for the distance coordinate will actually be greater than A0, and we're going to find that in a little bit too. Okay. It tells us here the result. The result should be that the expectation value of r, which is what we would expect to be the average, if we could measure that distance. If there were an experiment, there isn't, but if there were an experiment that would say, what's the radius of the electron right now? And we could do that experiment lots and lots of times. The average of them should come to be 3/2 A0, right? So it is noticeably longer than the point at the top of the curve, which is at A0. All right, I'm going to work through quickly and just illustrate the fact that those results should be the way that we said they are, right? So this is my probability function, right? The 4 pi r squared psi squared. So what we want to do is we want to find a maximum in that. First, let's take that and let's actually write over here what that would look like. I've got psi squared, and so when I square psi, I'm going to square this stuff, which means it's going to get rid of the square root, right? So this is going to be equal to that 4 pi. Then on the bottom, I'm going to have pi, I'm going to have A0 cubed, okay. And then I'm going to have r squared, and I'm going to have e to the minus 2r over A0. Okay, and that's what my probability function is going to look like. The pi's will cancel, so let's get rid of those. Okay, if I want to find the maximum in this, what do I have to do? I have to take the derivative of it, right? So I want this. I've got the constants in front of that, which are now 4 over a0 cubed. And then I've got pieces from taking the derivative of the r squared and the exponential piece. I get a 2r e to the minus 2r e to the minus 2r over a0. And then I get a piece which is minus 2r squared over a0 e to the minus 2r over a0. Right. If I take all that and simplify it a little bit, I can see that that's equal to 8r over a0 cubed e to the minus 2r over a0, all of that times 1 minus r over a0. And if we look at that, that goes to 0 it goes to 0 if r is equal to 0, which is the minimum at the origin. It also goes to 0 if r over a0 is equal to 1, which means it goes to 0 when r is equal to a0. Right, and so that is my my maximum in the probability density. So that's the most probable radius, right? That is, if I measured the radius lots of times, that is the value I would get more often than any other value, because that's what it means to be the most probable radius. Okay. Suppose I wanted to do the average radius, or the expectation value of the radius. I can do that one like this. The operator for the radius is just r. Right? So I take my wave function. The formalism for finding the expectation value says take the operator, in this case just r, sandwich it between psi and psi star, and integrate over the range of values. For r, that's from 0 to infinity. Okay. So if I put things in there, I'm going to get that my expectation value for r should be equal to, let's see, when I do the, I'm going to take the 4 pi out, and I'm going to have this piece squared again. So I'm going to end up with 4 over a0 cubed as the constant piece, and I'm going to take that outside of the integral, right? Then I've got an integral from 0 to infinity of what will be, I've got r in here, and I've got r squared, so I get r cubed. And then I've got the exponential piece, which is twice, so I get e to the minus 2r over a0, and then I have a dr, right? That's a reasonably standard form integral. If you wanted to, you could integrate it using, just substitute u as r over a0, I guess should work. I just used an integral calculator to say that the integral gives me 3 a0 to the 4th over 8. Okay, and that's the piece, that's just this piece. Right, so I have to multiply that by my 4 a0 cubed. So this is all equal to 4 over a0 cubed times 3 a0 to the 4th over 8. And when I do all that, I swear that's an a there. When I do all that, sure enough, I'm going to end up with 3 a0 over 2. Okay, so that is, if I took lots of measurements of the radius somehow, that would be the average of all of them, right? The most frequently gotten value would just be a0, but because there are some values that are much longer than that, the average will come out to be higher, and it will come out to be that value there, okay? it turns out that if I did r squared for this, I would get a value which is further still, right? So if I found the expectation value of r squared, I have notes over here that tell me I would actually get 3a0 squared. The reason for that, again, being that those longer distances, the long radius points, will raise r squared up even more than they'll raise r. Other thing that I'm going to mention in this video is the idea about uncertainty. And in fact, we're going to use the uncertainty principle in a moment to do another bit of calculating about a hydrogen atom, okay? The point at which we saw the idea of uncertainty before was somewhat incidentally when we looked at the free electron problem, right? When we had just one wave function, we did e to the ikx, then we had an exact momentum, and we had no information whatsoever about position. Okay, when I made the superposition of two wave functions, so I did a linear combination of e to the ikx and e to the minus ikx, the position began to be localized somewhat, right? There was an interference pattern, there were maxima and minima, there was some information in there about positions, but the momentum became less well defined, right? Because then the momentum was no longer an eigenvalue, and so we had two possible momenta for the two possible wave functions, and so we lost information about that, right? If we use more than two wave functions in our superposition, that trend would keep going, right? We would gradually get to have more and more information about the position in this case, and less information about the momentum. Okay, this is a generalizable result that leads to something known as the Heisenberg uncertainty principle, right? Which says it's written here in terms of position and momentum for a one-dimensional problem because that's the easiest case. It says delta x times delta p, where delta x is the uncertainty in position, delta p is the uncertainty in momentum. The product of those two things has to be at least as large as h bar over 2. Okay, and what that does is it says the more you know about the momentum or the energy of a particle, the less you know about its position. Okay, you could flip that and say the more you know about position, the less you know about momentum. I always think about it the first way because the energy of an electron in an atom, say, is the thing we can measure. Right? We don't really have an experiment that tells us this is where the position is, but we do have experiments that tell us this is the energy, right? And so the better we make those energy measurements, the less we get to know about the position, right? And that's kind of what's at the heart of the idea that we treat electrons in atoms as these delocalized, just smeared out charges, where we talk about the electron cloud, for example, around an atom. I'm going to use the uncertainty principle in a slightly peculiar way here, just to wrap up. I'm going to say the kinetic energy of an electron in a hydrogen atom can go as high as about 14 electron volts. If it goes higher than that, the electron will actually separate itself from the atom. That's essentially the ionization energy of a hydrogen atom. Okay, we're going to find the momentum that corresponds to an electron with an energy of 14 eV. And then I'm going to say, assume that the uncertainty in the momentum is about the same magnitude, the same order of magnitude as the momentum itself, right? Then I'm going to use the uncertainty principle to estimate the radius or the size of my hydrogen atom. Okay, it's a little bit an unusual thing, but it will show us that we can, in fact, do some calculating some things with the uncertainty principle at times. Okay, so the first part is just to turn that kinetic energy into momentum, right? And we have a nice simple relationship for that, which says that kinetic energy is equal to p squared over 2m, which means that p is equal to square root of 2m kinetic energy. And I'm going to want to get my kinetic energy out of EV and into joules. So let me just say, if I convert that to joules, we've used this number a couple times. There's 1.602 times 10 to the minus 19th joules in an EV. So this comes to be 2.2 times 10 to the minus 18 joules. All right, so if I take that and put that in there, I'm going to need also the mass of the electron. So this says that I have square root of 2 times 2.2 times 10 to the minus 18 That's the two kinetic energy. So I went out of order here. Sorry about that. The 9.1 times 10 to the minus 31 kilograms. That's the mass of an electron. If I multiply all that out, I will get 20 times 10, no, 2 rather, not 20. I get 2.0 times 10 to the minus 24. That's in kilogram meters per second. Right, so that is my my momentum for my electron at 14 electron volts. Okay, I'm going to take the order of magnitude of that. So I'm going to use 10 to the minus 24th power as my my delta p when I do the next piece. All right, I'm just going to use an order of magnitude because honestly, this is a fairly crude calculation, and there's no point in pretending it's got lots of meaningful digits. So if delta p is equal to about that much, I want to find what delta x is, this positional uncertainty, and I'm going to say that's the uncertainty in my radius. Okay, and so if I do that, my inequality said that delta x, delta p was greater than or equal to h bar over 2. So I'm going to take the equality point there, right? And I'm going to say that would give me something like delta x, which is what I'm going to use here to be delta r. At the point where those are equal, I'd say I'd have h bar over 2 delta p, right? Which is equal to h bar is about 1 times 10 to the minus 34th. Joule seconds. And again, I'm just kind of in orders of magnitude here. So down here, I've got a 2, and I'm going to put in 10 to the minus 24th for my uncertainty in my momentum. And if I do all that and multiply those out, what I get is I get about 5 times 10 to the minus 11 meters, which would be order of 50 picometers, which is actually right about A0, the Bohr radius, okay? And so it does give me a result that is kind of right in line with the size of that distribution function from the wave function itself, right? So despite the fact that that calculation is really primitive and we just, again, went for orders of magnitude all over the place, we get a result which is actually very much in keeping with what seems like the size of the problem in the hydrogen atom. Okay, that's a sort of a quick rundown of various aspects of things we can do for the hydrogen atom. It gives us a chance to take at least a look at how some of the tools we've been looking at could be applied to an actual molecule. Okay, going forward, next up, we're going to venture into what is chapter 4 of your textbook in module number 3. In that one, we're going to take up a variety of model systems. The first one is something rather curiously known as the particle in a box, which is arguably the simplest model that can give us a quantized system. And we'll work in some detail with that to get a bit more comfortable with what we can do with our quantum mechanical tools. Thanks.